Next speaker is David Paul McLean. The title is Lotte World Tower. Mr. McLean is the managing director of the structure team for the Lotte World Tower. He is an innovative and widely experienced structural engineer and has designed structures in Europe, Middle East, Asia, and the United States. His resume includes a wide variety of the building types from mid to high-rise buildings, sports stadia to airport and conference centers. Please.
Good morning, everybody. Thank you for coming. For a minute there, I thought I was going to have to use the box, but I'm quite pleased that I've actually managed to reach the microphone. I'm really here to talk to you about the progress for the project. As part of my slide presentation, I did include some information about the architecture and the structural design, but now I'll go through those rather quickly, as you've already seen them. Or if some people weren't paying attention, they'll get a second opportunity to look at the structure. As you know, the site is here in Songpa-gu in Seoul, just near the Han River. The way it's probably its best landmark is the fact that it's across the road from Lotte World, which everybody knows, and the Jamsil station is the easiest spot to get to the site. Again, like I say, you know most of the information so far on the structure itself, the architects, the structural engineer, the gross floor area, and it's a mixture of office, retail, hotel, observation deck. It's part of the tower itself is part of a large campus, and you can see there's quite a few buildings, low-rise buildings in and around the tower itself. Here's a couple of elevations of earlier designs. I'd have to check with the architect to see if there's many changes since these were taken. And again, another architectural slide showing you what the uses are: hotel, Officetel, office, retail, observation deck. This is one of the problems with coming third in the list. You find that some of your slides have already been discussed. The structure, I will just spend a little bit more time on this just to make sure. I'm going to talk about the outriggers later on, so I just want to make sure that you're aware of which levels I'm talking about. Specifically, I will talk about this elevation, this level here, and sorry, this level and this level, which are here and here, levels. Sorry, here and here, which are levels 39 and 72. This is our construction schedule. As you can see in the top corner there, we are at. Sorry. We are at this stage, so as you can see from the process that's going here, we haven't got, we're halfway through the substructure, and their completion date is 2015. So my discussion or presentation will be mainly about this area, and I'll also be showing you photographs of our current progress, and I'll be talking about some of the, or at least one particular issue that's quite important when constructing a super tall structure of this height. As you know already, the tower is situated on a raft, 6.3 meters, 6.5 meters deep. It's located in the this corner of the site, and some of the loads are listed there, but we've already gone through that slide before. Here is most of the work in 2010 was involved in excavating the rock from the site. As you can see, it's a very deep excavation. The whole site is going to be covered with 6 levels of basement, so the whole site has to be cleared of rock before the work can start. You saw this one earlier on. This is the site on 22nd of February, earlier on this year. One of the big things, one of the big jobs that was required here, as well as the normal construction of the tower itself, was all the temporary works that go into supporting the construction of the tower itself. If you're going to use the whole of the site for your basement, parking, shopping, etc., it doesn't leave you very much area to store equipment in, so you have to set up this extra floor for storing equipment and for deliveries. So this selection of photographs just shows you the quantity of steel, which I believe is in the order of over 11,000 tons of steel to support the structure, which will be removed once the structure is finished. Here we have later period. This is April, and as you can see, the temporary works are coming along nicely. The entrances for the lower level come in here, and we have an entrance here which eventually will bring us onto that level. During the process, during the construction of the temporary works, we were able to work on the reinforcing insulation for the mat itself. Here you see a plan view of it. The mat is, say, 6.5 meters thick, so you can imagine the height between the bottom steel, the top steel is quite large, so this whole framework had to be installed to support the top layer of reinforcement. As you can see, some of the lower reinforcement is it's very congested, there's a lot of it. And for the average person to lift the steel, it's quite difficult as well, because this is actually a 50 millimeter bar being lifted by about 9 people or so to get it into place. On preparing for the pour itself, there were a number of ways of pouring the concrete. We had these in situ pumps at the top level, up here at this level, which brought pipes down to the top of the mat for pouring concrete there. We also had these other pumps with the booms that are movable, and they were also coming from the top and some coming from the bottom. This here is a covering, like an umbrella, a tent for the mat itself in case we had any trouble with the rain during the pours and had to actually protect the workers and the concrete and the reinforcement. On the day of the pour, which started on the 4th of June, about 5 a.m., we have a view here of the trucks coming in, as I said earlier on, coming from here down into this location here. Also trucks coming across this way to feed the in situ pumps, and also the mobile pumps up here with the booms pouring the concrete. A few more views of the process during that Saturday. We see the trucks. This contraption here is actually an inflatable wall, which was there to reduce the noise from the trucks during the night, because it was an overnight pour, and we were trying to cause the least amount of problem to the neighbours. Here you just see some of the equipment again, and another view of the mat itself. When the pour first started, of course, you have a couple of people down here with vibrators getting the early stages of the concrete in, but eventually they builds up, and you end up hopefully getting out of it before it gets too deep. And it's just a few more shots of the pouring process. Here's a nice shot of the site itself at night. It gives a nice view of Seoul in the background as well, but it's just an attractive picture. Here we are the next day. On Sunday, we'd reached the top of the mat, and everything went pretty well so far. No real problems with any of the machinery or any deliveries. Some of the statistics for the pour. We have the mat size, of course, 72 by 72 approximately. There was 4,200 tons of reinforcement, 31,000 cubic meters of concrete delivered, and we had 5,200 trucks, which equated to about 2.89 trucks per minute. So it was a very, very busy 30 hours, but everything went successfully, and as you can see, the pour looks quite good from this distance here. It's just covered while the curing process takes place. And once the pour was finished, we now had all this space to use for all the storage and equipment I mentioned earlier on, bringing in supplies. So as I explained, we cannot use any of the areas around here. At the moment, there's no construction. Sorry, in the photograph, there's no construction there, but the intention was to put the rest of the low-rise construction there, so we can't store anything there. So everything's stored up in these locations. As you can see, this is August 29 this year. The work is beginning at the upper end of the site here. You can see the mud slab is in there at the moment. The number of cranes is increasing as the pace picks up. And here we have a lot more cranes, and again, more work here, and a lot of equipment and material waiting on the top to be brought down onto the mat itself. This is where we are currently. I just took these photographs a couple of days ago, and there's a view through the temporary work showing how far the core is at this stage. Just another view of the core showing the scaffolding for the workers. We have the climbing shores shown here, but you just started off. Up till now, we were able to get away with just sitting formwork on the mat itself, but now the formwork is beginning to climb, so we're attaching it to the walls and to the mega columns. Here's a view of the core. The top point here is actually the current level, and that's just daylight you can see coming through here. And here we have a couple of close-up views of the pressure system for the climbing forms. Another picture of part of the climbing forward, probably for, I'm not too sure actually what piece that's for. To make sure that everything is in the right place, we have a local reference locator on the building next door to us, which is taller than, well, much taller, of course, than the site. And through this, we can get our surveying equipment linked up with our GPS system and take all the measurements and details we need from on the site. If this one should go, this is purely Lotte's control point. If there's anything wrong with it, we do have the option of using a backup from the Seoul system, although this does have a delay system, whereas our own one is real time. At every 20 floors or so, we have inclinometers attached to the core walls to let us know where the actual building is at any time in 3D space, so we can marry it with the GPS signals we are getting. This is just a quick overall diagram showing how the system operates, from the satellites to the total station, to the formwork, to the floor levels, the core, offsets for grids, offsets for inserts, whatever is necessary. One of the issues big issues that's come up with it, or that comes up with very, very tall structures, is creep and shrinkage. As most of you are aware, shrinkage normally takes place with the curing of the concrete, and creep takes place over time with the load of the structure. These are just a few simple diagrams showing you what happens when one part of the structure, one part of the structure settles too much, or settles in a different rate than the rest of the structure. You end up with these kind of problems. Also, you end up with issues with the say moment connections here, the extra moments being induced into the floor slabs. To monitor the creep and shrinkage, we've set up a fairly complicated system. For the mega columns, we have 5 strain gauges in the mega columns. We've strain gauges in the main core walls, strain gauges in the lower columns that are on the basement floor, and strain gauges on the inner core walls. These diagrams just show the strain gauges and the access boxes located to allow for visual reading, or in this case, automatic reading. Horizontal movement, apart from wind and lateral loads, is also caused by the different functions in the building, because the mass of the building changes from floor to floor. So Midas IT, who are doing the work for the creep and shrinkage, produced this diagram showing the relationship between the stiffness center and the mass center of the building, showing the eccentricities. So these do have an effect on the lateral movement of the structure, which have to be accommodated. They provided a preliminary report for the expected creep and shrinkage on the building. And the way they report it is they have these grid lines between columns and between cores, and they pick a particular line, pick an elevation or settlement point, and give the values in these tables. The tables figures are fairly easy to understand. That this is the mega column, this is the core wall nearest mega column. This green line is the actual difference between the two values, the different settlement between them. And this dotted line here is the 50 millimeters is the required difference. When this is not achieved, then there's an issue, and compensation has to take place to get the column back into, or at least get this distance back into a reasonable quantity. Similarly for here, again, although I can't read them from that distance, I believe the core wall is the red and the mega columns are the blue. I forgot to mention, this part is the lower levels between B6 to 75. This part is 76 to level 106. This is the compensation approach being used. Here we have a typical example, only this time I think they've changed the colors just to make sure we're paying attention. This time the core wall is blue and the mega column is red, and we have this difference between them, and this again being the actual difference. This diagram shows compensating by bringing the column closer to the deflection levels, the settlement levels of the wall, which provides a difference here of, in this case, that's the 0 difference. So this would, sorry, this is actually, no, this is right. This is quite okay. This is within a reasonable amount. The one at the end, because my knowledge of Korean is not so good, I can't read these things, so I do my best to try and get them translated. Here we have overcompensation, and here we have less compensation. So with this one, you can see the difference is down to 0 along this line here, whereas here we can allow a more relaxed compensation for the relationship between the column and the megacore, the core wall. Here's just a simple diagram showing the sort of compensation that has to take place in the mega column in relation to the core. And the other area that becomes even, it's a big area of importance is the relationship between the core walls, the columns, and the outriggers. And they did a study in the Midas model, but the discussion for the next couple of slides will center around these two areas, these two outrigger areas. A typical section through one face of the core wall would show the outriggers like this. In fact, the outriggers actually go horizontally through the core wall as well. They're cast in, but they didn't show that under the report. And here you have a comparison of 3 outrigger connection scenarios. The first one at the top is no delay joint at the outrigger. By delay joint, what SAW team was alluding to earlier on was the not connecting the diagonal element of the outrigger up to its final connection at the top here until such time as the vertical shortening, or at least a good portion of the vertical shortening had taken place. So there's 3 the comparisons. These red lines are just the settlements at these points. The top one is no delay joint. The second one is the delay joint completed after construction is finished. And the third one is delay joint not operating permanently, which is not really a real case scenario. It's just, I presume they just included in the report for comparison. Here we have, again, two different levels, and what we're comparing here is the delay joint fully fixed. Delay joints are the ones in black. The fully fixed deflections are shown in orange. As you can see, the delay joint is working quite well. The fixed is that has, apart from the deflection side of it, the fixed joint has another issue which is very important, and that's the relationship between the forces in the diagonals when it uses a delay joint versus when there's no delay joint. And as you can see fairly quickly, the outriggers down here, 39 to 43, 72 to 75. The total forces, this is with delay joint, are along here, and the total forces without are shown over here. So there's quite a significant increase in the diagonal forces. There would be if it wasn't for the delay joint. This is a summary of what was found. I think I heard the bell, so I should go through it kind of quickly. After 100 years after lantern, which means actually 100 years after construction is finished, the average differential shortening is 4 millimeters. You can see for yourselves the different average differences. The lantern, 100 years after erection, will be deflected. It's likely to deflect X and Y, these dimensions, but they'll be compensated for during construction. The flat slab, the note there is just what I mentioned earlier on about the connections between the core and the column where the flat slabs connects has to be checked. Here we have differential shortening, 5 millimeters between mega columns and 28 millimeters between the inner and outer cores. This is how the schedule is being, or at least the monitoring is being performed. These diamonds, just the location strain gauges, these are compensation application, which means the additional height necessary to allow for the creep and shrinkage, and that's analysis. So during here, there's monitoring, then the red, it's the analysis, and once the analysis is done at here, the compensations are made. So you can see the compensation will be continuing all the way up all the way up for the life of the project. This just gives you an idea of, that's a picture of the strain gauges in the mega columns and in the core walls over here. They're different types depending on, there's ones that are good for heat resistance, some who are just plain, and some are for welding. I have a few slides just to show you where we are right now. As I mentioned earlier on, there's a lot more progress in the far end of the site. We're now standing on an observation deck at the tower looking down, and these are all the low-rise areas that we are seeing on the floor plan, and they're all getting their rafts put in right now. A closer view of the low-rise buildings. Another one. And finally, this one. Thanks very much.
Thank you, David. By going a little bit over time here, you've saved yourself from questions. So we're going to move on to the next speaker. But if you do have questions for David, please see him after the session is over. So we're going to move on to the next speaker.
The next speaker is Charles D. Clift. The title is Cutting Edge Technology in Building Reflectivity Simulations, Lotte World